All right, thanks, Cindy. Let me go ahead and just share a quick look at where's at the complex GitHub web page. So thanks everybody for joining us today. Glad you could make it. This talk is on data storage and file systems, and I'll sort of jump into the slides here in a moment. But I did want to point you to sort of like the most recent version of uh, a combination of the sort of data storage and file system talks, including data transfer that I gave recently. That's on the GitHub uh, for Complex. So I think that's in the, or maybe she hasn't put it in there, but I'll put the link to the GitHub in the chat there. And if you look down to the data management one, it's sort of a combination of our data transfer talk and this data storage and file systems ones. There's links to the most recent slides right here for the data storage and file systems. There's also some exercises that might be useful. Data storage and file system ones uh, mostly target this more files, more problems one set of exercises. So if you want to try some exercises afterwards, this is a nice place to look. I just went through these in the last 2 weeks and cleaned things up, and hopefully it's understandable and you can follow along there and do it yourself. Um, and the additional resources here are two previous recordings of the data transfer talk and this one, this data storage and file systems talk, and some additional older material on data management and file systems in general from some of my other colleagues at SDSE that we still have online. So if today doesn't sort of reach your expectations of all the material you want to cover, there's these additional resources here, as well as some of the tutorials you might be interested in. And this is sort of the most recent, like I said, set of exercises and things that I have here. Okay, let me stop that and share the slides. Let's see, in presentation mode. So I'll try to um, take some breaks along the way and check the meeting chat. So if you do have any questions, please do drop them in the chat as we go along. Unfortunately, we don't have some of our other colleagues from the Complex team today to help out answering those questions as I go. Usually we have one or two other folks answering questions along the way, but everybody's on vacation or out of the office today. So I'm sort of running this solo, but of course with the help of Cindy, Susan, and Shante in the background. So, okay, so let's go ahead and get started. So yeah, as I said, this is the data storage and file systems talk from the Complex training program. There's more links here. The short link here is to our Google Drive with all the slides from all of the different topics that we cover in the Complex program. And I forgot the GitHub link is right there. So if you get the slides, you'll have the link there as well. If you're not familiar with the Complex program, this is a training program funded by the National Science Foundation at SDSC to teach. The goal is to teach new users of advanced cyber infrastructure, like the high performance computing systems that we have at SDSE, how to use those systems effectively. So we have a bunch of different topics. If you're new to sort of supercomputing in general, this is sort of you're the target audience that cover things like parallel computing, Linux command line tools, scripting, batch job submissions, and of course, data management today. So if this is your first time, thanks for joining us. If you're returning Complex participant, thanks for joining us again. So this talk is intended to sort of be the first in a data management series that we've been putting together for the Complex program. We only have two sort of fleshed out right now, which is the data storage and file systems. Data transfer is the other one I mentioned. There should be links in these slides to the other set of slides as well. And I'm hoping to eventually work on a parallel IO one for working with parallel file systems. So yeah, that's overview of the series. And then today, the learning goals are really just to teach you what, some sense of what a file system is. What are some of the most common file systems you'll find in a high performance computing environment? Uh, sorry, moving the meeting chat around here. And so how you make decisions on which file systems you use and when you're working on HPC systems. And we'll hopefully get to talking about one of the biggest problems that we experience on file systems days when there's too much metadata being metadata operations that sort of impact file systems that you'll interact with. The prerequisite for this is really just the intermediate Linux and shell scripting uh, topic in the complex program. So hopefully you have a little bit of command line experience. You'll see some command line tools that you can use to sort of poke around and investigate the different file systems that you have access to. But yeah, that's about it. There's not something too complicated today. So this is the general overview of the talk. Um, so we're going to try to answer that question. What is a file system? We'll cover some of the different data storage devices and systems that uh, we store files on. Then we'll talk a little bit definitions of what really is a file, a directory, and something called inodes that are very important. And then I'll cover a general overview of some of the most common file systems that you might see attached to some of the resources you have access to. And then show you some quick example data, sort of hopefully hammering home like one of the main lessons I mentioned about metadata problems with an AI example, and then we'll just finish up there and take questions. Okay, so data storage, right? What is it, right? It's simply storing information, recording it on a storage medium, right? And as humans, we've invented many ways over the years of how to write down and store information on different storage medium, with going from, earliest examples to the latest examples, which we'll find in our high-end HPC systems or in our personal computers these days. Um, Now, when we talk about data storage, we're usually talking about files. And, one thing, there's some subtleties to what a file is on a computer system. It really is a resource for recording data on storage devices, right? It is sort of this abstract data structure that encompasses the information that was actually written to those physical storage devices we saw on the previous slide, right? Of course, files themselves have different formats for different types of data that you encode in different ways, and depending on how they're used. And the one thing, if you're not familiar with sort of Unix or Linux environments, is there's sort of this concept of everything is a file, and like the Linux systems are all HPC systems are effectively Linux systems. Don't know of any examples that aren't these days. If you look at the top 500 supercomputers in the world, I think it's 100% Linux, some flavor of Linux. And this diagram to the left here is sort of a nice graphic of showing you the subtlety of what a file is very different depending on the type of file it might be on a Linux system. When we talk about files and our data and the things that we interact with most of the time, we're talking usually about these regular files that store our text data, scripts, binary files, and things like that. We're also familiar with directories. You might be familiar with symbolic links, hard links. All might have seen some of this in some of the other complex talks if you've been to them. Um, but yeah, the Linux file system itself even talks to devices and storage devices, and so there's all this whole sort of different flavors of types of files you might see and interact with on on any given Linux system. But in general, we're talking about usually about regular files and directories is kind of what you interact with day to day, um, directly at least. And so, what is a file system? So, a file system is essentially the piece of software that provides the operating system a way to sort of create, organize, and manage access to the files on storage devices, right? It's sort of the intermediary between your general computer operating system and the piece of that that actually talks directly to the storage devices and keeps track of the abstract notion of the files on those storage devices, right? And with any given file system, regardless of the type, right, there's sort of a basic set of standard operations that you can, aren't probably too surprising. You can create new files, you can open files, you can read data from files, you can write data to files, you can close them, you can delete them, you can change who has access to your files and different attributes of the file that might be possible on that file system. Um, yeah, and so any file system you interact with, you kind of expect that you can do these types of operations on files. Excuse me. When we start talking about file systems, there's usually, and if you're new to Linux and things, there's sometimes some confusion with the file system hierarchy standards, which is sort of how it's not a file system itself. It's a standard. It's a convention of how the different directories and files in a Unix or Linux-like operating system are laid out and how they're used, right? So for you, the most common one when you log into like a high performance computing system is, usually when you log in, you'll be dropped into your home file system. So that's usually, or sorry, your home directory. And that's usually where um, all that you really need to care about on sort of the hierarchy, when you first start out, right? When you log into an HPC system, you have your home directory. That's where you can store your files and code and data and things like that, right? Yeah, sorry. I'm getting ahead of myself. Um, because as the slide, highlights, HPC systems are, multi-user systems. So your home directory is where your data is stored. Other people on the same system, it's a shared system, will have their own home directory with their directories and files that they own and as users of that system, right? So yeah, your home directory is sort of where you log in, where you install software, create scripts, get output from your jobs. Typically, though, the home directory will have a limited amount of storage available. I'm showing on the left, or sorry, on the right here, a snapshot of my home directory at some point in time from 2 years ago, I guess, probably. Uh, of on Expanse, which was one of our main production supercomputer at SDSC. We have 100 gigabytes of storage in the in our home directory, and so you don't usually have a lot of storage there. It's really intended for these purposes, like installing software, creating job scripts, storing some input data and some output data. Usually, there's other storage systems that will be available that if you need large amounts of data storage and different special types of maybe parallel file systems and things like that. If your code uses that, that'll be on a different file system. Um, yeah. So yeah, one of the big differences about interacting with file systems on an HPC system is it's usually your first experience with local versus distributed file systems. So every file, so there's lots of different types of file systems. The biggest sort of classification between the two I can think of is is local versus distributed. So a local file system is like the one you interact with on your laptop, in your basic operating system, like if you're using Mac or Windows or even Linux on your laptop, like me. You have a local file system that manages the files on, say, the hard disk in your laptop. right? It is the file system that your operating system sort of comes with and interacts with storage devices in the computer that are attached to the same system, right? Um, However, when we talk about interacting on a high performance computing system, right, there's many different compute nodes. There's multiple login nodes. So there's many different computers that you will interact with once you interact with that system itself. And so it's nice to have access to storage that can be seen across multiple devices, right? And so a distributed file system provides storage kind of in a file system as a service where you can share files across multiple storage devices over a network and attach that storage to multiple computers, right? And so in an HPC system, right, like your home directory can usually be seen from anywhere on the system, on any compute node, on any login node. You always see your home directory available, right? So that should hopefully be a hint that that's going to be usually a distributed type of file system, right? It's your home directory, but it could be on different types of file systems, right? And so, but it is definitely a distributed one usually because usually it's visible from anywhere, not just say the login nodes. So, uh, yeah, so one command, very simple command that has to do with starting to poke around and look at the different types of storage you have available on any given system is the df command. It just kind of reports disk space usage. And this is a snapshot from Expanse, just looking at some of the output. And as I just mentioned here, the arrow there is pointing to your home directories, or the home directory servers, as we call them. And you'll see there's actually multiple different slash home uh, mounts essentially, which are being shown here. So on Expanse, um, although everybody has a home directory, everybody's home directory isn't necessarily on the same physical storage node, right? So there are four different home storage servers that are attached to Expanse, and sort of we just allocate them round robin on any given when a new user is created, right? Just to sort of balance out the usage of those home directory servers. Now, um, so one of the things that you can experience is if you're working on an HPC system like Expanse here, um, you might notice that the file system, your home directory is acting funny, maybe uh, the response from running commands on the files that you have there are a bit sluggish, but your partner from your research group is on the same system and they have no problem. Well, it could be possibly that there's something going wrong with the home directory server that you're on versus the one that they might be on a different one that's not being impacted. And so this is can easily happen when a specific user that's sharing your home directory with you is behaving badly and using it inappropriately, right? In some way, they may be just sort of pounding on that that storage server in a non-ideal way that is impacting you, right? So that's why you want to learn how to be sort of careful about the types of storage systems you use and the file systems you interact with, because your actions can impact other people's work and performance and just general sort of user experience, right? And so these are shared systems, and so you want to try to be a conscientious user and community member to hopefully not impact others by um, misbehaving on the different file systems. And that's probably the most common thing that we see, just people behaving badly on the file systems, and it sort of hurts everybody else, whether it's their job performance or just sort of bring down the file system so people can't even access their data. These are things that happen fairly regularly. So it's a good thing to learn how to be a good file system user. Oh, okay. Uh, so skip over. Okay, so that's DF. So it kind of points you out gives you general information about different file systems you might see. Before I move on, though, any system you interact with, they should have a user guide, and they will likely explain all of the different file systems and what they want you to use them for. So that's also where you should find out information about the file systems. The df command is just sort of, the information Linux will present you about those file systems that they talk about in the user guide. So definitely always check out the user guide first, but DF will help you poke around and see a bit more of the details of what the layout is of the different file systems on the system you're attached to or logged into. Another thing that obviously is one of the most important questions people have is about the different file systems is how much storage do I have? And quota is a way to limit or set a maximum amount of storage that you can have on a given file system. Most file systems will have some quota set. Again, it'll likely say in the user guide what that quota is for sort of standard user account on that system. You may request and get allocated more storage for a given file system if your project requires it. One of the problems is because there's all different types of storage systems, and there's different ways that the system administrators and storage engineers will set them up and attach them to the HPC systems. There's not really a universal way to figure out how much storage you've been allocated and have in your account on a given file system. Yeah, there's just no you in how much you're currently using. There's no easy way to determine that per se universally. You'll usually have to go to the user guide, and they'll give you the specific commands or tools that you should run for a given file system to determine how much you're currently using and how much you have left. The only common one I think is on the next slide that in theory is, what you can do is with the du command. So the du is disk usage command. If you haven't used this before, it simply just runs through a given directory that you give it and will determine how much storage is being used. So if there is a universal command to figure out how much you're currently using, at least in a given directory on a given file system, this is how you do it. This is how we have to do it for users on home, because in their home directories, we don't have any other special command to easily determine what you're currently using. So if you have lots and lots of files, it could take a long time to run through your whole home directory. But if you really want to know, this is even what we have to do behind the scenes. Some of us who work on these systems day to day. Yeah, I think that's all I wanted to say there. So hopefully that gives you a decent conception of what a file system is. The different classifications of file systems. What I'll try to do now is run through the storage devices and systems. Yeah, and then we'll move on from there. So when we talked about files are sort of an abstract data structure that will track our information that gets actually written to different storage devices, right? These are the physical devices, physical hardware in the system that the data is actually written to, right? I feel like sometimes we forget that, there's real physical processes underlying, the storage, and that it's sort of it's so far abstract from us that we just expect it to always work. It doesn't always work that way. There are real limitations to the different hardware components and things that go into these systems. So this is a common diagram here that sort of shows what's known as the memory hierarchy. It sort of shows the trade-offs between sort of the capacity of like how much you can store in given storage devices, the performance, like how quickly can it read information out of those storage devices or read and write, how reliable that given type of storage device might be, and how scalable it is. And this is sort of, still a good relevant graph. If you haven't seen it before, it goes all the way from the individual registers, which are sort of the smallest unit of storage that are sort of on your, CPU chips themselves, right? As close as possible to the actual processing part of the chips. The next level is sort of the cache memory, and then you have sort of the main memory, which is sort of your standard RAM or CPU memory you'll have on your system. And these are what are called sort of the primary storage. Good if I have more on this on the next slide. Well, I'll go into the memory next week. Um, but these are sort of, the I get to the definition later. Volatile and non-volatile storage. So these are the volatile storage components. That means basically the power needs to be on for data to be stored in them. So that's not where we keep data long term. That's what sort of live data in flight that we're interacting with and computing on the computer, right? Those are that's the primary storage. The secondary storage is sort of the disks, right? The flash memory, traditional spinning disk, and sort of even tape we have still around. So that's what I'll talk about here just quickly. Yeah. So yeah, again, memory is sort of the one of the key, how much memory a given compute node has is usually one of the questions that you want to know when you're running your code on or doing some sort of analysis on the HPC resources. Um, and yeah, so this is, again, one of these primary storage components. Um, you know, and the limitation for you usually is how much it limits how much data you can, your application might require, the size of the memory will sometimes limit, depending on the application that you're using, how large, say, your simulation or data analysis can be. I ran into this recently, like I'm doing some data analysis on sort of a bunch of the data about the types of software people use on Expanse. And I was, setting this up, exploring the data locally on my laptop. But I have, lots and lots of data. And so I could only analyze, like, what was it? A single month on my local laptop, but I have probably, 24 or 36 months of data. So I'm going to have to probably take all that data over to Expanse and get a larger compute node with more memory, so I can, um, analyze more than a single month at a time on my laptop, because it ran out of memory essentially. But yeah, as I note here, certain software, you can use sort of these out of core algorithms, and there's usually, most of my links here are usually to like the Wikipedia pages if you want to dive in more on any of the topics mentioned, where you could use, part of your local disk as well for, as sort of a pseudo memory for some of this sort of data analysis like I was doing, where not all of the data is loaded into memory all at once. Yeah. But yeah, so the reason I start here with memory is also, if you are curious where your fastest quote unquote file system would live, you can also have a small file system on sort of what we call a RAM disk. And so I'll just leave that there. So if you're interested in using RAM disks for any local fast storage, check that out. Um, yeah, so the free command is, how you would find out how much memory a given computer you're on. has available, how much is currently being used, and how much is currently free. So here I've shown, I think, yeah. So essentially, I'm showing three different node types on Expanse. We have one of the login nodes, which is has a certain amount of memory and definitely a lot being used. And then we have sort of standard compute nodes on Expanse, which have about 256 gigabytes or so, uh, and uh, GPU accelerated compute nodes, which have a bit more, around 380 gigabytes. But yeah, so this free command is how you can sort of poke around and find out how much free memory there is on any given node. Again, this information should be in the user guide of any system that you're working on, but if you need to check yourself and get a better sense of how much is actually available versus what's printed in the user guide, that's the command. So yeah, as I mentioned, the world of storage devices sort of divided into primary, secondary, or usually also volatile and non-volatile. And so volatile, as I mentioned, just requires power to maintain stored data. Whereas non-volatile is the storage that usually you'll store your data long term, because that's where, after the power is removed, the data will be preserved on those storage devices. And so yeah, what are some of those more permanent non-volatile storage? So we still use a lot of spinning disk. So this is just a diagram of a traditional sort of hard drive that you would have found in many personal computers back in the day, not so much today. But we still use these spinning hard drives in many of the back-end storage systems for some of these file systems. And so it is still very relevant, sort of the physical limitations of spinning hard drives. Um, uh, the more expensive storage, though, that you'll see in HPC systems today is using solid state drives, like they're used probably in your laptop. Um, Most HPC systems and compute nodes will usually have a local hard disk like this on every given compute node. So it'll be sort of temporary scratch space. So if you really need the RAM for something else and you don't want to use RAM disk, this is kind of the next best thing. You'll have like a local hard drive, a local solid state drive on every given compute node with a local file system that you can interact with and use as sort of high performance storage that feels like storage that would be on like your laptop or your personal desktop computer. Because it's a local file system, local hard drive. Um, However, there are a lot of new file systems, which I'll mention briefly here at the end, that you might see attached to an HPC system. It'll be a distributed file system, and there'll be, solid state drive, NVMe drives as part of sort of a tiered storage system uh, in these more complex distributed file systems where part of it'll be spinning disk, part of it'll be solid state, targeting the solid state stuff for sort of the most high frequency operations that you might imagine are going on the file system. And then as sort of data becomes a bit colder and not as used as much, gets pushed to spinning disk, which is a bit slower. Uh, And yeah, the slowest medium for sure for storage is still magnetic tape, but it's still used widely in high performance computing and other applications. Access itself has, I think, now two tape systems. So I know there's Ranch at TAC, so Texas Advanced Computing Center. So if you, this is magnetic tape is used typically for archival and backup use cases, right? So you're not using this sort of um, for your daily storage on an HPC system in any way. But if you have important data that you need a place to back it up, and archive it. These are the types of systems that are out there that you can use. So yeah, there's Ranch at Tech, and I think there's a new one. I think it's called Granite at NCSA. Uh, I think I think that's true. I'll have to double check, but need to update these slides a bit. But yeah, Ranch is one of them. Because one of the key things and takeaways from today's talk is whenever you're using an HPC system, most in general, all of those file systems that you interact with, no matter which file system it is, there aren't backups. You are sort of responsible for maintaining the integrity of your data. We typically, on any given file system attached to our system, we typically only have one copy of your data. Uh, in best case, usually your home directory is backed up in some way, or at least there's a snapshot of it. And so we might be able to recover things if you accidentally delete them. But on all of our other file systems, where there's significant storage, like it's just too expensive to, you know, if you buy like, 10 petabytes of storage, it's twice as expensive to buy 20 petabytes to back that 10 petabytes up. So most of these high-end, large-scale storage systems that are attached to HPC systems, there's no backup. We have one copy of your data, and so whenever for your research, especially students working on your PhD or your master's thesis, you don't want to lose your data. You want to graduate, so be very mindful about how you plan to store your data and back it up somewhere else, besides just on all of these systems. Okay. Files, directories, and inodes. So yeah, this is sort of the lions, tigers, and bears definitions. Okay, so digging a little bit deeper into what a file is and what file systems consist of, essentially, is what this section is about. And typically, when we talk about file systems, we're talking about what's known as a POSIX file system. So this is just a standard that, well, I don't know if it's technically a standard, but it's definitely as close to a standard as you can think of, that most file systems will tell you how POSIX compliant they are. And this is, when you hear POSIX comply, POSIX file system, just think about like the type of file system you interact every day on the command line. It's, you see files, you see directories, you see need to do them, you can move them. This is what a POSIX sort of interface looks like to a given file system. But under the hood, right, it's a bit more complicated, and that's sort of what this diagram is sort of indicating here, that there's different pieces to every given file that are sort of important to understand it, that sort of a fundamental level at some point when you start thinking about what a file is and what a file is, right? So the block is the part that's sort of the physical record, right? And these are the bytes and bits that are written to those storage devices, right? But usually when these file systems organize the data on those physical storage mediums, right, there's a specific sort of block size, right, that's associated when data is written to them, right? And so POSIX file systems, yeah, sort of treated these as sequences of bytes. And so each block usually has a fixed number of bytes, this block size. On Linux systems, usually I think the default is 4 kilobytes. And so anytime you create a file, right, there's sort of a placeholder of 4 kilobytes waiting for all the data to be written to that block, right? So if you create a single bit of data in a file, your file system will still look at that as using up those 4 kilobytes, right? Even though you've only written a single bit of real data that you care about, right? Your one coin toss, right? So this is just sort of part of the structure of what's actually happening under the hood, right? And why that sometimes you'll see mismatches in what you think of how much storage you're using and how much the file system thinks you're using. come down to some of these quirks about how things are structured on any given file system. Okay, so that's the block. So that's sort of like the physical component. Uh, the inode is something that you probably haven't heard of if you're sort of new to Linux and file systems. But the inode is important because it's sort of part of the data structure um, that tracks the metadata about a given file system object, whether it's a file or a directory. Um, so yeah, inode stands for index node, and it really captures the metadata around any given file, right? So, right, some of the things that file systems track about files is, when the file was last modified, when the contents were last modified, when the file was last accessed, who owns it. Usually they belong to a Linux group, right? So there's a user ID, a group ID associated with a given file, and there's different permissions that you can allow on any given set of files and directories, right? And so all this metadata around there has to be tracked, right? And so how's that tracked? It's tracked in this part, this inode part of the data structure, in a POSIX file system. So, this is one thing that people don't commonly think about, right? Is in addition to how much, storage space a file system has for your files, right? Uh, there's data about those files. And so there's also a limit of how many um, you know, inodes there can be essentially, right? Because there's data that needs to be stored about the file. So there's usually not only a quota about sort of how many files and how much storage you can use, there's also usually a quota of how many inodes you can use on a given system, because you don't want your file system to run out of inodes, right? Because if you do, then no new files can be created, basically, right? Um, yeah, so it's just something that people don't think of, but it's kind of a part of the key part of the data structure. Um, More familiar though, right? Directories, but yeah, the one thing about directories is that they're a bit special in the sense uh, they're more sort of referential, so they actually reference the files that are in the directories, right? And so um, yeah, each yeah, like it says here, each POS file system has its own implementation of a directory. Um, but yeah, it's not. What do I want to say here? Yeah, yeah, it's not a file in itself, but it's references to files. So it's sort of the overarching sort of collection of how things. If you go back to this direct item here, so you have sort of the directory entry. So you can see here that this is sort of your different metadata, and then you have pointers to the actual blocks where the file is written. But then there's also references to the inodes to have the metadata about those blocks and the what files they belong to. And so the directory is sort of the organizing superstructure in some sense, object that uh, keeps track of things. Okay. And then, of course, yeah, a file is just a set of blocks, right? So you have that physical set of data on the storage mediums, but yeah, files are just a set of blocks on the storage device, and obviously, the file itself is and how to find it is stored inside the directory in the directory entry. So yeah, that's probably a little bit more than you actually need to know about, POSIX file systems, but it's good to have sort of the definitions. One example where you can see sort of this play out is on our Lustre file system on Expanse. We actually, Lustre, if you interact with the Lustre file system, there is a set of, special commands that you can use to query your quotas and things like that. And the example here is this LSF quota, where I'm looking at, in the first example, I'm looking at my storage on the Expanse Lustre Scratch file system. where it looks like I have, what is it, 12 million files and 15 terabytes used, but it doesn't look like I have any quota uh, limit there. And then I have in the group project storage, something like 16 million files, 50 terabyte quota limit on the total storage, 23 terabytes used. But you can see that uh, there's two sets of quotas and limits, right? What are those other quotas? Well, the left obviously is the total amount of storage that you're allowed, where the other quota on the right and limit on the right is actually on inodes. So that's like, right, this is a limit. You can limit on the number of files. So I don't have a limit on that account because I have sort of special user privileges, but on my test account, which is like a normal user account, you can see here there's actually a limit of 2 million uh, files on that Scratch file system. Anyway, so um, so that's sort of an inode limit placed on this file system. Okay, let's see, I'm doing okay on time, I think. I'll try to pick it up here so we can end at the top of the hour. Yeah, so the next section is really just a high-level overview of different file systems. Every HPC system is going to be unique and have different sets of file systems that you have access to. You're always probably going to have some sort of home file system, which I'll talk about here in a second. We use, on Expanse, we use the NFS file system. Uh, but there'll be usually other one or two other types of file systems attached for um, more performance use cases. Like we have Lustre, which is very good at writing and reading large amounts of data. And then we also have a Ceph object store, which I'll talk about in a second. But yeah, so every system is unique and complicated. Look at the documentation and figure out which file system are available and what they want you to use them for is always my case. Yeah, this is sort of the conceptual layout of an HPC system. I haven't shown it yet, but you have your login nodes, compute nodes, you have the internal networks. Then you have like the shared file systems where it'll be attached, data transfer nodes, management nodes. This is just reference for the different types of nodes in a given system. Here I'm showing the ext4 file system, which is just a local file system you'll see on most Linux operating systems. And so when I use the df command here, it also, I showed you earlier the Expanse home directories servers, but you'll see some of those, the type of file system is also listed. So those are just local file systems that are formatted for the ext4 file system. Then, as was shown here, we talked about the Expanse home file system. It's an NFS file system. So this is a network file system, right? This is one of these distributed file systems that allow you to share your data across multiple nodes. I like this diagram because it kind of gives you a sense of uh, uh, how distributed systems start getting more complicated, right? The local file system is just writing to a single disk attached to your computer. Now you have, say, a client, say you're on a login node, and then you have a server where your data is actually stored. When you write data in your home directory on a given HPC login node or on a compute node, right? Every file system interaction that you make, whether it's your code or you interactively interacting with the system, right? All of those calls to the file system are going out over a network to your storage server, getting the data, bringing it back, and displaying it on the client side, right? So there is this sort of layers of infrastructure between you and where the data actually is when you ask for it or read it. And so, there's going to be additional overhead, right? So these distributed file systems like NFS aren't going to be as performant as a local hard disk attached to the computer, right? It's just never going to be that performant, right? And so you have to keep that in mind that there are limitations to these systems because of this complicated orchestration that's going on underneath hood, even though everything looks like you're just, on the command line interacting with the system. So yeah, there it is on Expanse. And they only get more complicated. NFS is fairly simple. This is sort of a diagram of what Lustre looks like. There's multiple different types of servers. There's servers specifically for metadata versus where the storage is. It can get very complicated. Lustre itself is really designed for sort of writing out large files, reading in large files, like if you're doing things like weather simulations or reading large files of data. What it's not designed for is very tiny, small sets of files. So a lot of these AI data sets have, just really bad organization of how they've structured the data sets, just kind of like plainly laid it out on the file system with like millions of tiny images or something like that. It's really bad at um, interacting with those because you can see, again, there's going to be a lot of orchestration when you touch a file, right? You have to retrieve that metadata, right? Here, the metadata is a specific server that you're going to go to. And then once you have the metadata, then you can go find out where the data actually is on one of the object storage targets, right? So you have all this orchestration behind the scenes. So if you have millions of files spread out, multiple storage targets, and you're looking up metadata all the time to figure out where these tiny files are, it's not really what it was designed to do. But it's Lustre. It has its purpose. But yeah, it's kind of a pain because a lot of people have a lot of tiny files, unfortunately. One of the more common ones these days that is coming up is the Ceph file systems. So Ceph is sort of more complicated system. It has options for file system, POSIX-like interact file system, but it also has object storage, more like AWS, which is not really like a file system necessarily. It's sort of a different sort of storage modality. But the nice thing about Ceph and sort of its popularity, especially growing in HPC, is, as I mentioned, we don't have usually backups of your files. The one thing that's nice about Ceph is it does a pretty good job at preventing data loss through data replication. So there has some nice sort of ability to create some fault tolerance in losing data. So it's harder for us to lose your data. Whereas like on Lustre, if the disk where your data is stored in Lustre goes down, there's no way to retrieve it. Right? So you're going to lose your data if you don't have a backup. If a hard drive just fails for whatever reason, right? And you happen to be that unlucky person. Um, uh, but yeah, Ceph itself will prevent failures like that because it has this sort of replication feature. So if you have a Ceph file system on the system you're working on, it's like, yeah, it's pretty good. It's performance wise, I'll show you here. I mean, I think that from the ones that we've used, it's about as good as the NFS in terms of performance, and so it's a good robust file system. Yeah, just one of the more common ones. So you can see here we have Ceph file system on Expanse. But one thing to keep in mind, like I said, every HPC system will be unique. There's tons of the new file systems out there. Some of the more common ones you'll see these days. So IBM Spectrum Scale is kind of used to be called GPFS. Who knows? They may have changed the name again since I made these slides. I don't know. That's a pretty common one we'll see in the HPC space. BGFS a little bit. I think we have one customer that we run a system for that has that now. SDSC uses Cumula, which is just kind of a proprietary version of NFS. Same with Vast. Vast is very popular these days. It's nice operating system, but I think it's also NFS based technically under the hood. Weka is cool. Anyway, there's a whole suite of innovation in the file system space these days, different companies and things that you might see. So lots of HPC centers are trying out new file systems. So uh, you might see other ones. Okay, and just to end with no minutes left, is just to highlight an example of some study that I did. Basically, running a pre-process slide. Sorry, let me see if I can find this slide before we end. So yeah, so this is that slide that was blanked out on my other ones. And this is showing a study of taking this ImageNet data set and pre-processing that data with the scripts on different file system we had attached to Expanse on one of its compute nodes. And you can see here the range of runtimes of the same script being run on the same set of data. It's kind of wild, right? I mean, so if you look at the local file system, this local scratch, this is that solid state NVMe hard drive attached to the compute node in that node, right, itself. Sort of took a little bit under an hour. Here's the running the same test on the home file system. So from my home directory on NFS, took about a little under 10 hours, looks like maybe 8. Um, uh, on the Expand Cluster file system, some of those initial runs were up to 100 hours, which is kind of crazy. So you go from under 1 hour doing the pre-processing on the local hard drive in the compute node versus just trying to do the same thing on the Lustre file system. You're talking 50 to 100 hours, which is you can. This is why it's important to use different file systems for their intended purposes. But in this case, it's also about the data itself, right? So this data is just like a million images laid out in a bunch of directories, right, that get processed, right, into um, some other files essentially for the training the model itself. Um, so where you sort of unzip a million files, matters when you're processing things, right? So if you have data sets like that, definitely be careful like what file system we're working on. But regardless of what type of data you're reading or writing, or you want to think about what file system am I on and how is that data actually laid out, and is that appropriate for this type of file system? And this is sort of just the proof that it can really matter and affect your performance if you're not careful. Anyway, so I'm gonna stop there. I'm already over by about a couple minutes. So thank you for joining us. If you have to take off, if you want to stick around and ask some questions, I'll be here.